Hi there, it's physical science coach Powers, and today we're going to be learning about forces once again. We're jumping into chapter 12.1, and today we're going to talk a little bit about Newton's first and second laws. So let's just go right into it. I think you guys are going to enjoy the content here today. So our objectives are to be able to state Newton's first law of motion, which is tied closely to inertia, and then give examples of it. And then to use Newton's second law of motion to calculate force, mass, and acceleration. Basically, second law is like an equation, and so we'll just look at how that one works. All right, so let's look at the first law. What makes an object speed up, slow down, or change directions? Think about it. Okay, here's an object. Oh, maybe here's an object, and I want it to move, right? We've talked about this before. In order to move an object, you have to apply a net force, right? So objects change their motion when there's a net force applied. Now, this is considered Newton's first law because if they do not have a net force applied, then they do not move. And this is kind of the idea behind inertia, right? So when we state Newton's first law, we usually state it this way. An object at rest tends to remain at rest, and an object in motion tends to remain in motion, unless acted upon by an outside force or an unbalanced force. Now here we have a hockey puck. If you guys have played air hockey before, it's a little air hockey puck, and gravity would be wanting to pull that thing down, and the air is pushing it up, right? So it is going to remain at rest. Now, this is a great little scenario. If you guys have ever played air hockey, you guys can know how you can touch that object just really, really, really lightly, and it moves pretty easily, right? Well, it stays in motion. It stays still even when there's this force pushing up on it because it's balanced the gravity. The air and the gravity have balanced each other, so it's just kind of hovering there, right? And so it doesn't move until you touch it. Now, once you touch it, it begins to move. So the unbalanced force is your hand pushing that air hockey puck out of the way. And it stays at rest until acted upon by an outside force, in this case being your hand, right? So this is a good example of Newton's first law. We can also think about it in terms of, spaceships and stuff, but let's just kind of go on with some of the more practical applications right now. All right, so inertia is defined as a tendency of an object to remain at rest or in motion, depending upon which it already is, with a constant velocity. Okay, so it might be at rest, constant velocity equals 0, or it might be in motion. You can maybe think about it, that spaceship that's flying through space, and it's going to have its constant velocity if no other outside force is acting upon it, right? Now, how does this have to do with your everyday life? Well, think about seat belts, car seats for babies. Why are they providing protection? Well, remember that when your car comes to a sudden stop, your body wants to continue in motion. The car's motion has suddenly been stopped, but your body wants to keep in motion because objects in motion will remain at motion unless acted upon by an outside force. So that seatbelt is acting as an outside force to stop your body from moving through the windshield, for instance. Okay, so you got to make sure to wear those seatbelts, right? Because you want to keep your body's inertia from taking you outside the car and being in danger by hitting the road and things like that. So that backward force is pushing you back into the car seat. Now remember, the objects that have more mass have more inertia. So it's going to be hard to stop a locomotive in comparison to a bicycle, right? Something that is traveling at the same speed but is more massive, has a lot more inertia, is going to cause a lot more damage. And so, getting hit by a bicycle while you're in a car wouldn't be a big deal, but getting hit by a locomotive while you're in a car, big deal, right? So inertia has to do with mass, but they're not the same thing. Remember, mass and inertia are not the same thing. It's just a greater massive objects or more massive objects are going to have greater inertia. Okay, and that also means their tendency to stay still is going to be a lot greater too, right? They have greater inertia to not start moving. It's going to take more force to start moving them. All right, so let's look at Newton's second law now, and then we'll give you some diagrams to kind of see and how these things all tie in together. So think about Newton's second law. What does this all mean? Well, it's a formula, but we want to explain kind of what is behind that formula before we show it to you. So we start by asking ourselves this question: what determines how much an object is going to speed up or slow down? All right. So if you have a little baseball and you punch it with your little finger there, what's it going to do compared to taking that thing and chucking it with a full arm swing, right? What determines how much an object is going to speed up or slow down? Well, it's the force that you apply to that object, right? And it's how big that object is that will determine how that force affects that object. So if you have a really big object, a really massive object, then that little force isn't going to do anything, right? But if you have a really small object, that little force could do a lot. And so you have to think about these three variables and how they're connected to each other: force, mass, and acceleration. Okay, so this is principles. This is Newton's second principle. It's his this principle is Newton's second law. And again, it is force is equal to mass times acceleration. All right, the net force, how much force you have to push on something, is going to be equivalent to the mass of that object and how much it accelerates as it's moving through space. All right. So how do we measure force? Well, you're probably familiar with measuring force in terms of pounds, right? That is the way that we typically talk about how gravity is affecting our mass. And so we say, oh yeah, I'm 150 pounds, right? That's how much force is being applied from your body onto the scale, okay, because of Earth's gravitational pull on your mass. And so in the metric system, in the SI system, we use the term Newton, all right? A Newton, capital N, is something that tells us about force, just like a pound would do that in the English system. So you wouldn't measure your force or your weight in kilograms. If you're doing it correctly with the SI system, you would do it in newtons. And what is a Newton equal to? A Newton is equal to 1 kilogram times 1 meter per second squared. So basically the kilogram is the mass, and the meter per second squared we learned about last chapter was our acceleration, right? So it's a Newton. A Newton is a kilogram meter per second squared. It's taking that mass and how fast can we accelerate it. Okay, so again, our units here, if we're talking about units of measurement, let me go ahead and pull my pen up here real quick. Woo! And we'll go back to that screen. Let's make sure that we can talk about the units that we know. All right, so we've got our force is, again, we want you to know that we're measuring things in newtons here. You know, what we're familiar with here in the States, what we kind of use is we're using pounds, but really in the English system, they don't even actually use pounds to talk about force, but that's kind of what we're kind of familiar with. So we're going to use newtons, okay? Mass is in kilograms. Okay, and then the acceleration, we've talked about this already, is in meters per second squared, right? So a Newton is equal to, and we just saw this on the last screen, a kilogram meter per second squared. Just kind of show you a slightly different look for that. And again, that makes sense because we have force is equal to mass, that's the kilogram, and then times acceleration, which is the meters per second squared. Okay. Now, there's a lot of different practice problems that you can practice this with. If you want to open up your book to page 401 and practice questions number 1 through 4, then that would give you a good chance to practice some of these equations. Okay. But we're going to go ahead and skip through that right now. This is a pretty basic equation. We've done equations like this now, and I think we're pretty familiar with it. So let's go ahead and skip forward and give you some examples here. All right, so for equal forces, a larger mass accelerates less. So if you look at these two football players, we're talking about equal forces. And the reason that we're talking about equal forces here is because we've got two players, right? So there's two players, the same players, applying the same force, okay, in both examples. But because there's no other players on this one, then this is able to have a greater force. These two players here are weighing down, or they're adding mass to the whole sled that they have to push on, and so it's not going to go as fast. So if you have equal force, a larger mass is going to accelerate less with that equal force being applied. If you look at this example, here we have a VW bug that's getting pushed. Look at how many people are pushing it on this side, right? We've got a greater force. You've got like 3 people pushing on it over here, whereas on this one, you've only got 1 person pushing on it. And so it makes sense that if I have an equal mass, in this case, the mass is the VW bug, then if I apply greater force with more people, it's going to get going faster. And so we're trying to show you here that this acceleration arrow, that purple arrow, is bigger than that purple arrow. Okay, you're going to get greater acceleration with a greater force being applied to it. Okay, so let's, before we go back to that little review there, I want to look at a problem and give you a chance to practice this problem, right? So here it says calculate the acceleration. So let's go ahead and do this. I'm going to go ahead and change colors again. Oh boy, just went forward and went the wrong spot there. I want to calculate the acceleration. Now, I don't want a highlighter. I want a yellow pen. Give me different ink color, man. Thank you. All right. Calculate the acceleration. That's question mark. That's what we're looking for. We know acceleration is typically in meters per second squared, right? If you were talking about the acceleration in the English system, you might be talking about, or the common system, you might be talking about feet per second squared. It says you have an 82 kilogram couch. All right. So that's going to be our mass. And then you have a force of 21 newtons. So our formula is force equals mass times acceleration, but we're looking for acceleration. So we got to rewrite our equation to say that acceleration is equal to force divided by mass. All right, since the mass is divided by both sides there. And so then we just write that out. Acceleration is equal to 21 newtons divided by 82 kilograms. Now remember, a newton is equal to a kilogram meter per second squared. And what I love about all of these units in physics is you can just say, oh, well, the kilograms get canceled out. And so what am I left with? A meter per second squared. That's acceleration. So 21 divided by 82 is going to be your answer in terms of how much acceleration you have in meters per second squared. Okay, so that's how you would do that problem. All right, so let's look at what we have learned in this section. Okay, so what makes an object speed up, slow down, or change directions? It's got to be acted upon by a net force, right? And so force is going to make an object speed up, slow down, or change directions. What determines how much an object speeds up or slows down? The amount of force that we apply and the mass of that object, right? Both of those things are going to determine how much it speeds up or slows down. Now, the speeds up and slows down part, you probably are recognizing now, we're talking about acceleration, right? So two things affect acceleration, the force and the mass. All right, so that's all we're talking about today. It's a pretty quick and easy lecture, 12.1. I hope you have an awesome day. I hope you learned some cool stuff today. And God bless you. Be kind to one another. Checking out for today.